Okay, first of all, thanks. I would like to thank the organizers of this event for the invitation. Of course, it's a pleasure to be part of this very interesting seminar series. I've seen the previous seminars. They look all very interesting. So I hope this will live up the expectations. Okay, and of course, I look forward to visiting the IHES in person at some point. All right, so because this is a mixed audience, right, comprising mathematicians and physicists, I've decided to turn my seminar into somewhat a higher level introduction to some of the research questions I'm interested in, right, on quantum many-body dynamics, thermalization, ergodicity breaking, and this kind of things. Yeah, so I will discuss my research results only in the last part of the talk. And so my hope is that this kind of seminar can stimulate interesting discussions across diverse components of the audience. Okay, so let's start. So first of all, this research, so we talk about non-equilibrium quantum many-body dynamics, right? So this research field has been inspired, or one should say revived, by the latest generation of experiments with the so-called synthetic quantum matter platforms, right? So here you find a non-exhaustive list on the slides from ultra-cold gases to superconducting qubits and so on, right? So this term synthetic conveys that our experimental colleagues have achieved the ability to control, to manipulate, and to image a large number of particles like atoms or photons or electrons, really without compromising the coherence of the many-body quantum state, right? So just to give an example, some of these experiments have now demonstrated the preparation of a Schrödinger cat state. So for example, a few tens of particles coherently prepared in a quantum superposition of macroscopically distinct wave functions, right? So this is something that the founding fathers of quantum mechanics would have likely considered as science fiction 100 years ago. Okay, so these synthetic systems have new unique features, right, which make them fundamentally distinct from traditional condensed matter systems, right? So in particular, they can be considered well decoupled from the environment, so they realize coherent quantum mechanical evolution, right? So then their characteristic space and time scales are comparatively very large, right? And this allows experimentalists to control and to monitor the system with single particle and real-time resolution, okay? And importantly, the interactions are largely programmable. So we have a programmable Hamiltonian for the system. And nowadays, we can even think of interspersing quantum mechanical evolution, so unitary evolution, with measurements and feed-forward operations. So this gives rise to a new kind of non-unitary interactive dynamics, we can call it. So because of these unique features, we can say that synthetic quantum matter realizes a new paradigm in quantum many-body physics. So one reason to call it a new paradigm is that these new features allow us to interrogate the system with a new set of fundamental questions, right? Particularly revolving around the notion of thermalization and non-equilibrium states of matter, right? So what is thermalization, right? So thermalization is basically the statement that an isolated system dynamically approaches thermodynamic equilibrium, right? So this is a basic phenomenon that we all experience in everyday life, and it is also the fundamental assumption of statistical mechanics, right? It's the zeroth law of thermodynamics, if you wish. But the point is, how much can we trust this assumption in the context of synthetic quantum matter, which, as I argued in the previous slide, is very different from ordinary matter, right? So from a theoretical viewpoint, let's imagine an array of quantum particles or spins prepared in a simple, uncorrelated initial state, right? And evolving in time governed by some interacting Hamiltonian, right? So evolution is modeled as unitary, right? Because we said that these systems are well decoupled from the environment, so they realize coherent quantum mechanical evolution of an isolated many-body system, right? So it's governed by the Schrödinger equation. So evolution is modeled as unitary, so the global wave function of the system, right, is just rotating forever in Hilbert space, right? So what does it even mean that the system is approaching thermodynamic equilibrium, right? So what we mean is that when we monitor local portions of the system, we expect to see relaxation to a thermal equilibrium state, so to values of the observables compatible with the predictions of some thermal equilibrium ensemble. right? Possibly governed by some universal relaxation law at long times, okay? So the questions here are essentially, how does this relaxation happen, right? And how do we predict and compute large-scale hydrodynamic data, right? Like dynamical critical exponents or transport coefficients. And especially, are there systems which evade this expectation, right? So systems that don't reach thermal equilibrium and possibly realize a richer set of non-equilibrium phases of matter, we can call it, right? So these are general questions in the field. Okay, so we can distill a pretty clean mathematical formulation of the problem, right? So in particular, we want to consider a system with n degrees of freedom, right? N particles, if you wish, where n will be sent to infinity, right? And we want to consider an initial state, ρ0, right? Typically, we are only interested in physically meaningful states whose preparation, roughly speaking, whose preparation uses only a finite amount of resources, right? And then we consider a dynamical evolution, so a Hamiltonian flaw in mathematical language. And importantly, crucially, we must consider a subspace of relevant physical observables, okay? So in classical mechanics, a state is given by a probability distribution in the phase space of n particles. The Hamiltonian flaw is generated by the Lie derivative acting along the vector, the Hamiltonian vector field, so the Poisson bracket in physics language. And the observables are functions of phase space, right? And typically, as relevant observables, we choose to look at smooth observables in phase space. Now, in quantum mechanics, instead, a state is given by a positive and trace normalized operator on a composite Hilbert space of n particles, right? And the Hamiltonian flaw is generated by the adjoint Hamiltonian superoperator, so the commutator in physics language, right? In the quantum case, it's a bit less obvious what are the relevant observables, right? Because there is no natural notion of smoothness in Hilbert space, right? So observables are by definition linear operators, right? So in the limit of large n, one typically considers local observables. So by local, we mean observables that only depend on a finite subset of the degrees of freedom, okay? Now, the statement of thermalization, then, it is entirely expressed by this equation, right, that you see in the frame, right? So basically, for every finite system size n and every finite time t, right, the expectation value of an observable OA, right, is perfectly well defined, right? It's a computable number that depends on n and t, right? And then we can take essentially the thermodynamic limit. So we'll look at how this number behaves as we take the limit of large system size. And if this limit exists, which is quite generally true under some mild assumptions on the initial state and the Hamiltonian, then we can look at how this value changes in time, right? And if this observable settles at long times on some stationary value, right, we can compare this value to the expectation value of the same observable in an appropriate thermal equilibrium ensemble. And thermalization is the statement that these two things are the same thing, okay? So notice that in this approach, we haven't invoked any time averaging, right? Because we chose to look at time evolution of infinite systems in a sense. So this choice automatically eliminates the problem of Poincare recurrences, right, which are always there in finite systems. So you see that this choice is not exactly equivalent to the classic ergodic problem, right? And there is a good reason for this discrepancy, because ergodicity, in a sense, is neither necessary nor sufficient for this criterion, right? So we can give a couple of examples. So in certain ergodic systems, for example, mathematically ergodic systems, ergodization time could blow up as the system size increases. Now, this is typically the case for glasses, for example. So in this case, the system is mathematically ergodic for every finite size. However, this does not comply with our definition of thermalization. And on the other hand, it might be that there is some crazy, extremely complicated integral of motion, right? That this thing exists, but is not visible in local observables. Somehow, when we only look at expectation values of local observables, what we see is completely transparent to the existence of this crazy integral of motion. So I don't know of an explicit example of this, but this is certainly a theoretical possibility. So in this case, the system would not be ergodic in the mathematical sense. However, it would comply with our definition of thermalization, right? Okay, so this is our criterion. This is the statement one would like to make progress on. Good. So so there are basically some research strands of investigation associated with questions arising from this problem. So one research strand has been on finding generic conditions on the Hamiltonian and on the initial states such that the thermalization ansatz holds true, right? So I would like to insist on these generic conditions because a theorem has actually been proven. Here you see the reference on the slide. That the problem of thermalization is actually undecidable from a computer science viewpoint, right? So given a precise initial state and Hamiltonian, it is undecidable whether the system reaches thermal equilibrium. But we can imagine, in principle, to relax this strong assumption that we know the Hamiltonian and the initial state perfectly, right? And we try to prove instead some statement for ensembles of states and ensembles of Hamiltonians with large probability, right? And there has been some interesting work in this direction in recent years. Now, another interesting strand of investigation concerns the thermalization time, right? So essentially, how much time does it take for a system to reach thermal equilibrium, right? In particular, it is interesting to prove lower bounds on the thermalization times for certain classes of Hamiltonians. And I will show you some examples in the next slides. And finally, as I mentioned before, it is extremely interesting actually to understand under which conditions thermalization breaks down completely, right? So here you see examples of how this can happen. For example, our preferred set of local observables could settle at stationary values at long times, but these values fails to comply with an appropriate equilibrium ensemble, right? This is one possibility, one scenario. The other scenario is that the values of local observables don't settle at all, right? They keep their time dependence for longer, even infinite times, right? And there have been discoveries of mechanisms why these things can happen, right? I will not discuss this in detail, but this is another interesting strand of investigation in this field. Okay. So basically, in classical mechanics, as probably some of you know, or maybe many of you know better than me, right? So rigorous progress has proved extremely hard, right? And on the other hand, it's fair to say that brute force numerical simulations are available in classical mechanics. And by contrast, in quantum mechanics, brute force numerical simulations are fundamentally out of reach for computers, right? And even, one must say, even non-brute force numerical simulations of non-equilibrium dynamics proved largely elusive so far. And on the other hand, there has been some really interesting recent progress on the theoretical side along all the three problems that I listed above. Okay, good. So I would like to review some of this part of this progress that I anticipated, right? So to make things a bit more concrete, so let me introduce a specific model, right? So a prototypical model in this field is given by quantum spin lattices, right? So we consider a lattice of n quantum spins, each of size s, capital S, right? Where capital S can be 1/2, 1, or even higher values, right? 3/2, and so on. So when S goes to infinity, the quantum many-body dynamics of the spin lattice, of the spin system, becomes the classical dynamics of classical spins. Okay, so in our prototypical Hamiltonian, right, we have generalized interaction tensor between spins. So sometimes this is called an XYZ spin Hamiltonian, right, which refers to the fact that we have interactions between the X, the Y, and the Z components of the spin with certain coefficients, right, that parameterize the anisotropy between the various axes, right? And then it's in general an external field that I call H here. So the range of spin-spin interactions is parameterized, is determined by this matrix Jij here. That maybe I can use my pen here. Yeah, so probably you see my pen. So this matrix Jij, right, which describes how strongly spin at site I interacts with spin at site J, right? So typically this Jij is a function of the physical distance between site I and site J, right? And it decays in some way with the distance. Now, a simple protocol to study non-equilibrium dynamics, so to study all these questions that I discussed before, is the so-called quantum quench, right? So which consists in preparing the system in the ground state of the Hamiltonian for a given choice of parameters, right? And then studying its time evolution governed by the Hamiltonian with a different value of the parameters, right? So physically, this corresponds to a rapid change in time of some of the parameters in the Hamiltonian, right? And by the way, this kind of Hamiltonians and this kind of dynamical protocols, like the quantum quench, are very naturally implemented in experiments, right, with synthetic quantum platforms, and are routinely investigated experimentally these days, right? Now, motivated by the experiments, the natural subspace of relevant physical observables, the one that we use to define all these questions on thermalization and so on, these are given by spin operators supporting a given local region of the lattice, which I denote A in the slide. Okay. And here you see again repeated the statement of thermalization for local observables, right? So this is what we discussed before. And if we require that this equation holds true for all possible observables supported in a local region, this is equivalent to the requirement that the reduced density matrix of the system in this local region essentially approaches the reduced density matrix of the corresponding thermal equilibrium ensemble. So this is a convenient way to state thermalization with a single equation, right? So the fact that all local observables relax to thermal equilibrium values is equivalent to the statement that the reduced density matrix in a local region attains the reduced density matrix of the thermal ensemble. Okay, good. So this is the setting, right? Now, what is the appropriate equilibrium ensemble that we should put there, right? To check these things. So because we only care about local observables, that's the choice we made, right? So it is natural to expect that the equilibrium ensemble, the appropriate equilibrium ensemble will be sensitive to the existence of local conservation laws, right? So specifically, imagine that there is a set of observables Q alpha, right, which can be expressed as a sum over the lattice of operators with finite support, right? So if the Q alphas commute with the Hamiltonian and commute among themselves, then a natural ansatz for the appropriate equilibrium ensemble is the so-called generalized Gibbs ensemble, right? Which is expressed as an exponential of a linear combination of the conserved operators with appropriate Lagrange multipliers that depend on the initial state, that will be fixed by the initial state. Okay. And now, if the Hamiltonian is the only conserved quantity, as it happens in generic systems, then the equilibrium ensemble is just the conventional Gibbs ensemble, just the exponential of some number times the Hamiltonian, right? This number is identified as the inverse temperature and all the things that we know. So this is the generic situation, right? However, if the Hamiltonian has multiple conservation laws, for example, in the model that I discussed in the previous slide, when we have, for example, vanishing anisotropy in the xy plane, right? Then we have rotational invariance along the z-axis, and then the magnetization along the z-axis is a conserved quantity. It commutes with the Hamiltonian, right? So in this case, we have an additional multiplier for the magnetization, right? And in particular,
Question?
Yes, please.
Alessio, Cedo. I mean, the model here is likely non-local at the end, right? Because you are assuming these couplings to be somehow well, decaying with the distance in some way, right?
Right. Well,
So
it depends. So if they decay sufficiently quickly, I think this is
yeah,
everything turns out to be the same as when the interactions have a finite
yes.
way.
But but are you making this assumption now or not? Are you
Well, for
assuming
now,
that
I'm not proving anything, right? So I'm allowed
yeah,
to assume.
I'm just asking whether there is so what you're saying about this conservation equation and the fact that
Oh, right.
you can define these objects, this Q to be somehow some local object in the way that you defined. I mean,
Right.
it is
Oh, no,
very
that's
sensitive to this, no?
yes. No, that's a good question, actually. I think the theory is more somehow. So, okay, let me put it this way. So all the things that we have more control on, so the things where the theory is more established, regard where the cases where the interactions are strictly local, right? the range of interaction is strictly finite. Now, when we believe that many things carry over when the interactions have extend to infinite distance but decay very rapidly, right? Now, when the interactions don't decay rapidly, I've actually worked a lot on these cases, but then I don't think it's very clear how to generalize this construction, for example, right?
Okay, very good.
I haven't seen this question in the literature.
Okay, thank you.
Yeah, no, it's an interesting question. Thanks. Yeah, so many of the things that I'm saying, actually, almost all of the things that I'm saying are just physics conjectures, I would say. So, and in many cases, these are incomplete, and so some of the things I will say later are actually rigorous theorems, but they apply to a certain specific class of Hamiltonians that I will discuss. So yeah, on this general level, I think many things are not completely known. So the things that you asked, I think, is one of the gaps probably in the, as far as I know. I mean, I may be missing some references, but yeah, as far as I know, this is not completely settled.
Mm-hmm.
Okay. Okay, so I was saying that if the Hamiltonian is the only conserved quantity, then we have a conventional Gibbs ensemble. If the Hamiltonian has multiple conservation laws, we have additional things in the generalized Gibbs ensemble. And in particular, integrability of the model comes with infinitely many such conserved quantities. Right? When we have infinitely many linearly independent Q alphas, then yeah, this is typically the case when we talk about integrability. Right? But also, this could be smaller. So it could be that we don't even conserve the energy. Oh, there is a question. Maybe I will finish this sentence and then we take the question. So if we don't even conserve the energy, for example, because the Hamiltonian is time dependent, as in the case, for example, of periodically driven systems, right? Then the appropriate equilibrium ensemble is a completely unstructured ensemble. So the identity matrix without any multiplier. There is nothing to fix, right? Okay, yeah, please, there is a question, I think.
Yeah. Okay. Can you hear me?
Yes, I do. Thanks.
Okay, good. Could you elaborate on the classical limit indicated on the next slide?
Classical limit? What do you mean?
On the next slide.
On the previous slide, you mean? This one?
Yes. Yes,
Okay.
the classical limit. What does it imply about the behavior of the system as the action becomes very large?
So you're asking about the limit of when the magnitude, the length of the individual spins goes to infinity.
Yes.
Right. Okay, no, this is actually, so okay, in the dynamics of a single spin, basically you can pretty straightforwardly see that there is an effective H bar, which is the inverse of the spin length. So basically you can recast the dynamics of a spin lattice with an effective H bar that is suppressed by capital S, right? So in the limit of large S, essentially, if you take the limit of large S first, this becomes a classical Hamiltonian. I mean, I cannot now, but it's kind of a yeah, it's a known fact. Yeah.
Okay. Thank you.
I should derive it for you. I can't now, but yeah, it's a fact. Take it as a fact, right? The limit of large spin length coincides with the classical limit for spin systems.
Okay.
Yeah, okay, maybe one intuitive way to see this is that so the phase space of a spin of a spin is the Bloch sphere, right? So that's the phase space. For example, you have canonical coordinates, which are SZ, the component of the spin along Z, and the conjugated angle, right? These are a choice of possible canonical coordinates on the phase space, right? And then essentially, when a quantum spin is as finite S, you can view the quantization of this problem as basically the fact that you're only allowing finitely many trajectories on the sphere from a semi-classical viewpoint. I mean, you have finitely many trajectories which have area 1 over S, right? You're dividing the surface of the sphere in S parts, right? For example, for spin 1/2, you have only two things, right? And then basically the limit of large S coincides with the limit where the patches in phase space have an area which go to 0. And this area in phase space is nothing but the effective Planck constant of the problem. Maybe this will added more confusion than, sorry, I don't know if this clarified. Anyway, so this is a well-known thing. You can look it up. Okay. Right. Okay, so we were here, right? And then what do we expect for the dynamical relaxation of the system, right? So we have this, depending on the conservation laws and depending on the structure of dynamics, we have different cases, right? So for example, in the absence of any conservation law, right, when the dynamics is fully fully chaotic, right? Meaning that there is no coupling to any slow quantity in the system, to any conserved quantities, then the expectation is that local observables relax to the equilibrium value, which is just 0, right? Because there is no notion of temperature, right? There is nothing is conserved, right? So expectation values of observables relax to 0 exponentially in times, right? And this the rate of this exponential defines appropriately defines the thermalization time. So this is the simplest case. In completely chaotic systems without any conservation law, we have this, we expect this exponential relaxation law. And this is like, in a way, this is like saying that the system acts as a self-generated self-generated thermal bath on itself. So if we look at a local region of the system, right, this is like a small system in contact with a bath, right, and it relaxes exponentially to the stationary state, right? Okay, so this is the simplest case, right? Now, when we do have conservation laws, for example, we have energy conservation, right? So energy density is a transported quantity, is a conserved quantity that can only move around, but is not created and not destroyed, right? So in this case, if we look at local observables which have an overlap with some of these slow quantities, so for example, with energy density, then we expect that these quantities do relax to some equilibrium ensemble, but this relaxation will be sensitive to the large-scale effective field theory description of the system, which is some effective hydrodynamic description of the system, right? So there will be some relaxation law that is governed by some exponent that is characteristic of this universal, so some algebraic tail that is witnessing this hydrodynamic description over large scales. And the coefficient, right, this capital D here, okay, if in the simplest case, Z, the dynamical exponent, is just 1/2, right? It's just the diffusion. So this is just the diffusion equation, and capital D is just the diffusion constant. So these are the data somehow of the effective field theory description of the non-equilibrium dynamics over large scales. And typically we expect that then local observables are sensitive to this hydrodynamic hierarchy. So they will couple to some hydrodynamic operators, and therefore in their long time relaxation, we will see some algebraic tails. Okay, so this is the generic expectation when the system does have conservation laws, right? And now when as in the sketches that I showed previously, when the system does not so fails to approach thermal equilibrium, so there is a complete breakdown of thermalization. In this case, we expect that the distance from the equilibrium ensemble will not go to 0, right? Will stay constant, or even it will continue fluctuating in time. It will keep some time dependence for long times, right? So this is, in this case, we talk about strong or weak ergodicity breaking, depending on whether you have to make an effort to choose a particular initial state that does this, or generically for arbitrary initial states, you will observe this kind of behavior, right? And there are, as I anticipated before, there are known, well, we sort of have some mechanisms now, we recognize some mechanisms that produce this behavior, right? Which is very interesting. Okay, so this is the scenario, right? Now, the simplest scenario where we have some slow dynamics, so some lack of approach to thermal equilibrium for parametrically long timescales, is the so-called pre-thermalization scenario. So let me describe what this means, right? So imagine we have a system, right, described by a Hamiltonian H, which is a perturbation of a Hamiltonian H0, and H0 has certain conservation laws, right? And the perturbation V, right? So we have this epsilon that parameterizes the strength of the perturbation, and V, the perturbation, breaks these conservation laws. So H0 commutes with a certain operator Q, right? But V does not commute, right? So the global Hamiltonian does not commute with V, so we expect that it will relax to an equilibrium ensemble that does not contain this conservation law Q, right? Because it is not conserved, right? However, it's easy to imagine that over short timescales, the system, so the perturbation will kick in because it's weak. It will kick in only at later times. So on short timescales, it is legitimate to somehow to expect that the system will relax to a sort of quasi-stationary equilibrium ensemble governed only by the part H0, right? So the expectation in this case is that there will be some quick relaxation to a quasi-stationary state, which is a weakly deformed generalized Gibbs ensemble, which contains this additional Lagrange multiplier associated with this weakly broken conservation law. And then there will be a slow drift of this state eventually towards the Gibbs ensemble, so where this extra conservation law is sort of broken, right? So the Lagrange multiplier will flow to 0 at long times. So in pictures, well, this is what we expect, right? So if we look at the reduced density matrix of the system of a subsystem of the system, right? So of a local region A, as I argued before, right? So from the viewpoint of the evolution of this local reduced density matrices, we will see that different initial states that have the same energy, for example. So when epsilon is strong, right? So when the system has no resemblance with the system with a conservation law, then all the initial conditions with the same energy will all flow to the same equilibrium ensemble, right? Which is some Gibbs state associated with some temperature, right? So there is a complete sort of irreversible erasure of information from the viewpoint of the reduced density matrix. And this is nothing but what we called thermalization before. However, when the system is close to a system with an additional conservation law, we expect a different scenario. So as I argued, we expect that different initial states will flow to different generalized Gibbs ensembles that are described by different values of this extra parameter, right, associated with the extra conservation law, right? And only over a longer time scale, this generalized Gibbs ensemble will drift. So the drift here is represented by this orange arrows, will slowly drift to the Gibbs ensemble. So the eventual state at long times will be the same. However, the relaxation dynamics will be very different, right? There will be an initial stage of pre-relaxation to some other non-thermal ensemble, and then this non-thermal thing will drift to the thermal ensemble. Okay, so that's called the pre-thermalization scenario. And now, what is the thermalization rate? So what is the speed of this drift, right? So this has been studied in a few semi-rigorous works, I would say. And basically, the generic expectation is that the speed of this drift is generally believed to be order epsilon square, right? So basically, you should view this as a kind of Fermi-Goldner rule in the space of reduced density matrices. Okay, so this is the sort of the general scenario, right? But under special circumstances, which I'm going to discuss now, the dynamics can be much slower. So it is generally a question of whether how slow can we make the thermalization, right? So as I argued before, it is interesting to put lower bounds, so to look at certain classes of Hamiltonians where we can establish lower bounds on the thermalization rate, right? Because this allows us to stabilize for very long times some non-thermal equilibrium, some non-equilibrium state, some non-thermal state, which allows us to circumvent the constraints of statistical mechanics and have a richer family of states, possibly with more interesting properties, right? So this is the goal. Okay, so one setup where this has been sort of established rigorously, right, is the following. So when we have a Hamiltonian which is a perturbation of a Hamiltonian, which has a very special form, which is a sum of local commuting operators, right? So every Hamiltonian H0, which is sum of local commuting operators, can be recast in the form of linear combination of some operators, that I call an alpha here, that can be called generalized number operators, right? So they can be written as sum over the lattice sides of some operators that are local, that have strictly finite support, and have integer spectrum, so that you can think of them as counting local excitations in some sense, right? And these numbers all commute with each other. Okay, so I will give an example, but just to make this a bit clearer, right? So okay, but assume we have a Hamiltonian of this form, right? Sum of commuting terms. So this is sort of a trivial dynamics, right? Because everything commutes, right? So you could call this a classical Hamiltonian, right? And now we introduce a generic perturbation. So this V is a completely generic perturbation, right? Okay, now the things become interesting in the following choice of parameters. Essentially, when this the coefficients in front of this number operators, right, are completely incommensurate. So mathematically, you require a Diophantine condition. So basically, this is a request that the frequencies appearing in this unperturbed Hamiltonian are as incommensurate as possible. So this Diophantine condition technically is expressed in this form where x is a vector of integers. And basically, it's a request that by taking integer combinations of these frequencies, you can only approach zero quite slowly, right? So it's not easy to make a linear combinations of these frequencies with integer coefficients and get close to zero, right? So this lower bound is expressing mathematically this request. And so you should think that, naively, you should think that these frequencies are requested to be very, very incommensurate, with irrational ratios among themselves. Okay, and as I said, the perturbation is completely generic, other than the fact that it's supposed to be it's supposed to be weak, and of course, in general, it will not commute with this number operator. So it will destroy this. It will destroy this sort of integrable structure of H0. Okay, so in this, so let me just give you an example just to make things a bit clearer. So if we can consider a Hamiltonian of the form of a quantum Ising model, right? So we have essentially Ising type interaction. So you see this Sx plus r. So this is an Ising interactions between spins at a distance r, right? And in general, we can take r. So for example, the nearest neighbor, the conventional nearest neighbor quantum Ising model would have only nearest neighbor interaction. So sigma SZ between nearest neighbors, right? And then we may have an external field, right, as Z, which is, okay, now it has coefficient B, right? Okay, so this is a classical, this is a classical Ising model, right, with Ising type interactions. Just it's a bit, so we have taken the liberty to have additional Ising interactions, say with second nearest neighbor, third nearest neighbor, up to some range, capital R, right? Okay, so this is a Hamiltonian that is a sum of commuting terms. It's a classical Hamiltonian, right? And in this case, we can recast this Hamiltonian in the form of sum of generalized number operators, right? So these number operators, for example, can be defined in the way you see on the slide, right? So basically, we want to recast the spin operators, which take value plus minus 1. We want to recast them as operators that take integer spectrum. So up to some reshuffling, the Hamiltonian can be written in the form that you see on the left, right? With this choice of number operators. And the perturbation, okay, in general, the simplest perturbation you can think of is some transverse field, right? So this doesn't commute with any of these terms and generates a completely non-trivial quantum dynamics. Okay, so this is just to give you an example. So in many cases, we are you could think of this family of Hamiltonians as interesting Hamiltonians, right? So perturbations of classical Hamiltonians. Okay, now in this case, you can prove an extremely powerful result, right? which is the fact that under a quasi-local unitary transformation U, I will discuss what it means, right? Then this canonical transformation can be constructed order by order in the perturbation, right? And basically in this rotated frame, so in the frame associated with this canonical transformation, the transformed number operators commute with the Hamiltonian. Sorry, there is a typo here. Commute with H, not with H0. So you can make this transformation in such a way that you suppress the commutator at all orders, right? And this allows you to prove an approximate conservation law of this dressed number operators for extremely long times, right? So to make things a bit more precise, essentially the theorem is the following, right? So this was proven in a simpler case by Abanin, Derouk, Ben Beito, and François Huveners in 2017, and then later generalized in this form by Derouk and Verret, right? So the theorem is that there is a unitary transformation U such that the transformed Hamiltonian takes the following form. Basically, it has the unperturbed part, H0, then it has a diagonal part, diagonal meaning that it commutes with H0, so it conserves all the number operators, right? And this can be done order by order, as I said before, up to a certain finite order that we call an optimal order, right? And then there is a rest. So everything that comes out of this construction basically comes from the higher order terms, can be put in this operator R, right? And now the statement is the following, that D, essentially this part D commutes with the number operators. So basically, if it were not for this rest R, this transformed Hamiltonian would exactly conserve all this generalized number operators, right? So we have Q of them, and all of them are conserved, right? And but however, because of this rest, so the entire game is basically to put a bound on how big this rest is, right? And the power of this result is that you can show that this rest is suppressed faster than any power in the strength of the perturbation, right? So this is kind of, it's very interesting because by using a perturbative construction, you eventually find a non-perturbative lower bound on the thermalization rate, right? And now this construction that is done order by order essentially preserves locality. So what does it mean? It means that this quasi-local transformation U is close to the identity. Meaning that if you transform local operators, so operators supported on a single site, for example, or on a finite region, essentially the support of this operator grows only locally, right? So it transforms local operators into local operators, and that's very important because now basically this defines a meaningful transformation, right? Okay. So basically, the key point, I will not review the proof of this result, but the key point of the proof is that basically this Diophantine condition on the frequencies of the unperturbed Hamiltonian allow you to control all the small denominators that appear in the perturbative expansion and allow you to put a lower bound on how quickly the magnitude of this rest order by order explodes, right? So basically, what you want to avoid in this perturbative expansion is the appearance of resonances, right? Because this is what makes your this is what is detrimental to your conservation laws. But because of this incommensuration, essentially you are able to prove that the smallness of the perturbation wins over the smallness of the denominators, right? Okay. And there is also, yes, please.
What is this K norm?
Oh, thanks. Yeah, that's a technical point. So this is, I think it's just a technical thing that is involved in the proof. So basically, it's a norm that keeps into account, measures how the size of the tail of the operators, right? So basically, it gives an exponentially decaying weight to operators that have bigger and bigger support. So essentially, keeping track of this kappa norm, right, it allows you to keep track of the how big the operators become after this transformation, in a sense. But I think it's a technical point. I think perhaps it's. I mean, I just wrote it because I didn't want to write wrong things on the slide. But yeah, I don't think it's worth discussing this now, right? But it's a technical point that is important to prove the result. But yeah, for the simple phrasing and interpretation of the result, I think you can forget about that. Okay, and there's a version of this result even for driven systems. So for systems that are periodically driven, yeah, okay. So in that case, you can make a similar rigorous statement on how quickly, well, how slowly thermalization is attained. Okay. So basically, for example, in the context of the model that I introduced here, for example, for when you perturb this classical Ising model, right? So basically, the statement is that, for example, consider the case where you have only nearest neighbor interactions, right? So the conventional Ising model, right? So in this case, essentially, the number operators that basically tell you about domain walls, right? So this number operator is 0 if there is no domain wall and 1 if there is a domain wall locally, right? So basically, this is telling you, okay, the classical energies just counts the domain walls, right? And then you put upon a generic perturbation that doesn't commute with the number of domain walls. So you expect that the number of domain walls will not be a conserved quantity, right? So you can create and destroy domain walls by the perturbation. But what this result is telling you is that because when the perturbation is small, is weak, basically for a time that diverges faster than any power of the perturbation, so again, it's a non-perturbatively long time, right? There is a dressed version of these domain walls that is conserved by the dynamics. So only eventually, after an extremely long time, you will see processes that create and destroy domain walls. But otherwise, this dressed conservation law is a good quantum number in a sense. This is the physical meaning of this result. And if you have multiple, so if you have first nearest neighbor interactions, but also second nearest neighbor, third nearest neighbor, and so on, then you have generalized domain walls. So you have domain walls between nearest neighbor spins, but also domain walls when you frustrate a bond between spins at distance 2, or you frustrate a bond between spins at distance 3, and so on and so forth. All this number of frustrated bonds at a given distance, they are all conserved for extremely long times, right? And this is, of course, a pretty strong statement on the relaxation dynamics of the system, because it is preventing these conservation laws are preventing the system from reaching thermal equilibrium, right? Because in the thermal equilibrium ensemble, you wouldn't care about how many domain walls or how many frustrated bonds are there. You would only care about the total energy, right? There would be just temperature and that's it, right? Now, basically, this is a dynamical obstruction, right? Because you have to conserve all of these things, right? Then you are prevented from reaching thermal equilibrium for extremely long times. These are all lower bounds, right? So we don't know what happens, at a rigorous level. We don't know what happens eventually at infinite time, right? Of course, what we expect is that at infinite times you do thermalize, you reach the Gibbs ensemble. But this is a mathematically controlled way of putting a lower bound on how. But okay, if it takes you longer than the age of the universe, okay, then maybe we shouldn't care about thermalization, and this is interesting physics, right? Good. Okay, so I discussed this. Now, in this last minutes, basically, I want to discuss some interesting consequences of this this rigorous prethermalization theory, right? And one interesting consequence that exists is the following. So if we have, okay, I consider again this model that I just introduced. So this classical finite range Ising model perturbed by something. So perturbed, for example, by a transverse magnetic field. Okay. Okay, so you can call this a variable range, one-dimensional quantum Ising chain. So quantum because of the perturbation, because the transverse field generates non-trivial quantum dynamics, right? and variable range because we are considering spin-spin interaction, easing spin-spin interactions, extending over some range capital R, right? Now, the physics of this model, the equilibrium physics of this model is well known, right? In particular, we know that the ground state of this model has spontaneous symmetry break. So this model, okay, has symmetry, the easing symmetry under flipping all the spins. And the ground state of this model is spontaneously breaks this symmetry. So we have two degenerate. So when the transverse field is sufficiently small, right? So there is a critical value of the transverse field below which the system spontaneously break this easing symmetry, right? So we have two degenerate ground states associated with two opposite values of the magnetization. And for stronger fields, then we have a paramagnetic phase where the spins are not, so when the symmetry is restored, and okay. So we want to consider the ordered phase, right? So for weak transverse field, the system does have long-range order and magnetization in the ground state, right? So imagine imagine you start you look at time evolution of the order parameter. So imagine you prepare the system in one of the magnetized ground states. So for example, in the simplest case, you can start from the ground state for epsilon equals 0. So without any transverse field, just the classical easing model, the ground state is just all the spins up or all the spins down, right? Now imagine, for example, you prepare the system in the state with all the spins up, right? And now suddenly you quench. Okay, so let me first discuss. So for when you have long range interactions, actually, this spontaneous breaking of the easing symmetry persists even in excited states, right? So you have a thermal transition when the interactions decay sufficiently slowly. In particular, decay slower than 1/r². Right, but okay, I will not be concerned with this. So the point I want to make is that if the interactions decay very slowly with the distance, then when you perform a quantum quench, right? So you bring the system out of equilibrium. If this quench is not too violent, so the energy density of the state after the quench is not too high, so you're effectively below the thermal transition point, then you will thermalize, but you thermalize to an ordered state, because there are finite temperature ordered states, right? So in that case, the persistence of the order parameter in time after the quench, so this is not surprising, right? Because even if you do reach thermal equilibrium, the thermal equilibrium state can have order, right? However, if you, as in the case that I'm considering, if you have only short-range interactions, in particular, I'm considering interactions extending over a finite range R, right? Then, in general, in excited states, there is no order. So as soon as you are away from the ground state, the system loses. So the thermal equilibrium state is disordered, right? So okay, when you quench the system out of equilibrium, you expect that this initial magnetization that you have on the ground state melts, right? Because if you do thermalize, the thermal state doesn't have any order. So if you monitor the time evolution of the order parameter, this starts from, okay, I forgot, I didn't put a sketch here, but this starts from a finite value, for example, 1, if you start from the state all up, right? Then you evolve the system in the presence of a magnetic field, so this order parameter will start to deplete, right? And if the system does thermalize at long times, this order parameter should go to 0, because we know that in the thermal state there is no order parameter, there is no order. So the order parameter is 0. So you restore the symmetry dynamically, right? This is the expectation. And in particular, you expect this decay of the order parameter to be exponential with a certain rate, gamma, right? Now, the point is that this was some numerical observation done in numerical simulations a few years ago. So there was some puzzling results in the sense that even if the interactions decay faster than this 1/r², right? So even for when you don't expect order to persist in dynamics, to persist in out of equilibrium, instead it seems to do, right? So you look at the dynamics of order parameter, and it seems that this does not decay to 0. So this was a numerical observation a few years ago, and essentially what we what we were able to establish, right, in our work in this work that you see on the slide, actually including Andrea De Luca, who is in Paris, we were able to establish essentially how this decay rate, using essentially leveraging this rigorous pre-thermalization theory and building on it, we could establish the following set of results, right? So in particular, okay, in the nearest neighbor model, where you have only nearest neighbor spin-spin interactions, okay, in that case, the model is even solvable, so you can do this calculation even exactly, and you can show that this...
Alessio, sorry to interrupt you, but we are a bit out of time, so we can perhaps go towards
let me just wrap up.
Okay.
Let me just wrap up these results that you see here in the frame, right? So basically, we could establish the following. So for the nearest neighbor quantum is in chain, this you can solve the model exactly, and you find that this relaxation rate of the order parameter scales like the third power of the transverse field. Okay, so no surprises so far. However, when you have longer range of interactions, right? So when your interaction extend over some finite range R, under the assumption that this couplings are incommensurate, right? So basically, here is where the rigorous pre-thermalization theory enters. Basically, you can rigorously prove the fact that the order parameter becomes exponentially long-lived. So the rate of decay of the order parameter basically explodes exponentially with the range of interactions, right? So it scales like epsilon to the 2R plus 1. So in the case R equal 1, you retrieve the exact results, epsilon square. But in general, this will explode exponentially with the range of interactions. And in particular, this led us to conjecture that when you have interactions that extend to infinite range but decay faster than this 1 over R square decay, so order should not persist at infinite times. Basically, if you leverage the theory that we lay for this for the case of finite range interactions, basically this leads you to the following conjecture that is written here, where the thermalization rate scales faster than any power in the perturbation. So basically, the picture is that you have very long-lived ordered state. Even if you don't, in the thermal state, there is no order, then the order parameter becomes extremely long-lived. Okay, I think I can stop here since we are a bit over time. So thanks.
Okay, so thank you very much for the very nice talk. So if there is some question from the audience or from well, either online or in person, please well, speak now. I cannot see anything from IHES. People from online. Okay, well then thank you very much, Alessio. And so we are going to have a big break, and the next talk is going to be at 12. So I'll see you at 12. Okay.
Okay. Thank you for having me.
Thank you very much, Alessio. Bye.